Now, for the presentation for tonight, we have Professor Wittman from UC Davis Physics and Astronomy Department here. And I'll hand it over to you. Thank you.
Great. Okay, so I'd like to talk to you about observing dark matter in the wild. By that I mean dark matter is some kind of particle that particle physicists are used to being able to manipulate particles, collide them, do what they want with them, see how they react. Dark matter, we can't do that because we don't have samples of dark matter in the laboratory. So we have to just observe what it does when it's outside the laboratory and try to make inferences from that. So I know you guys have heard about dark matter before, so I hope this isn't too redundant. Want to take a fresh look at, I'm not going to assume that you're all convinced that dark matter is real. So I wanted to look at a few case studies from the history of science. And we'll go all the way back to 1781 when Uranus was discovered, and it was quickly realized that the orbit of Uranus did not obey Newton's laws of gravity. If you put in, the known positions and masses of the sun and the other planets, they didn't quite work. And so you could ask, why doesn't this work? What do we need to tweak to be able to explain the motion of Uranus? And so there are two basic explanations offered. One is that there's an unseen planet perturbing the orbit of Uranus. And so you can think of that as like the, very analogous to dark matter. So there's some mass out there that we can't see that's perturbing these orbits. The other idea thrown out was like, hey, Uranus is unimaginably far from the sun, right? How is it possible that Newton's law of gravity still holds way out there? So let's tinker with the law of gravity and see if we can change it and explain that. And so a kind of more abstract way of thinking about this is we can change our auxiliary assumptions. So we leave alone the law of gravity, but we fiddle with the details that go into applying the law of gravity to modeling a specific situation. Or we say, hey, the whole unifying theory needs to be tweaked. All right. So when we think about this, physicists often use this term Occam's razor. It's like we prefer the simplest hypothesis that explains the data. You may not want to throw out Newton's inverse square law because it explains this enormous array of data of all the other planets and tides and so on. But so it really depends on exactly how the data is departing from the model and which, whether you prefer to modify the central theory or the auxiliary assumptions. In this case, this is a really fascinating story to me. So Leverrier was a theorist who said, if there's an unseen planet perturbing the orbit of Uranus, I can figure out where it should be. And he was completely unable to convince the observational astronomers in France that they should look for this. And he got really frustrated and he turned to some German astronomers and they found it within 1 hour of starting their search. Just incredible. So it did turn out in this case, Newton's law of gravity is correct. And the problem was with the extra assumptions that you need to make to actually to match real data. Okay, the second case study was that by the start of the 20th century, it was known that Mercury's orbit also didn't exactly match Newton's law of gravity. So Mercury's orbit is a very highly exaggerated version of Mercury's orbit. It precesses, and most of its precession is due to gravitational tugs by Jupiter. But a little bit of it was left over that couldn't be explained by gravitational tugs of Jupiter. So again, in this case, you can say, well, which solution are we going to go for? Well, the unseen mass works so well in the case of Uranus. Why don't we propose that for Mercury? And this has the additional advantage of it's really hard to see things near the sun. So if there's a planet really near the sun, maybe that's the reason we haven't seen it. But we can also tinker with the law of gravity. So in this case, maybe you might go straight for the unseen matter explanation, but it turns out that it's modified gravity explanation, right? So Einstein came up with his general theory of relativity based on completely other considerations, making gravity consistent with relativity. And it gave slightly different predictions for Mercury, and it completely explained the anomalous precession. So there's the two case studies that I want you to keep in mind when we talk about dark matter. Okay, so the basic motivation for us believing in dark matter is that we find these mismatches between observed orbital behavior and the orbital behavior you would predict by, from the amount of known mass. So we have this stars going around the center of a galaxy. We can tell pretty well what the how many, we can count the light from all the stars in the galaxy. We know that a certain amount of luminosity from the star corresponds to a certain amount of mass in the star. We can calculate how much mass there should be based on what we see, and it completely fails to explain the orbit. We need to have more mass in there to explain the orbit. And we see this in all kinds of contexts. So what are we going to do about it? Should we try to, we can propose dark matter, or we can try to find a modified theory of gravity. So just to make it a little more specific, the origin of this is with Fritz Zwicky in the 1930s. So this is almost 100 years old. That he looked at the velocities of galaxies and the cluster of galaxies, and they were way too fast for the amount of mass that that should be in there based on the amount of light. So these clusters should be flying apart because the galaxies are moving too fast, but they're not. Also, the kind of the standard issue that people start with when they present dark matter is galaxy rotation curves. So the fact that, this is the observed velocity of stars as a function of distance from the center of the Milky Way or any other disk galaxy, and it should go down once you are looking at stars that are orbiting outside most of the other stars. The velocity should go down, but it won't. So you need to invoke dark matter to explain that. And there's many other contexts in which we find this kind of mismatch between what you would predict from the gravity of the normal matter that we know that's there versus what's actually observed for gravitational behavior. So one way to get a slightly different, to have more confidence in our mass measurements is gravitational lensing. So the thing about many of the arguments that I outlined are based on assuming that an object is in a nice stable orbit. So back to this cluster here. You could, if you wanted to say like, well, the high velocities of galaxies are because the cluster is in fact flying apart, but it just, in our lifetime, you wouldn't actually see the difference. So there's an assumption there that what we're looking at is kind of a stable equilibrium. In the case of lensing, though, it's a technique that can measure the mass that doesn't care about whether an object is moving. So in this little cartoon, the observer is here, there's some source of light in the background, and the mass of this cluster of galaxies is strong enough to bend the light, and we can see multiple images. We can see one through the center maybe, and one on this side. And the cool thing about this is that it tells us the mass of this object without referring to any assumptions about its dynamical state. And I brought a couple of lenses with me that you can play with afterwards. So it turns out that the stem of the wine glass is a really good model for this. I'll put these out so we don't forget this. You can play around with these and hold them up to the light, and you can make, if you get the light to be right on the axis, you'll see a ring of light, very bright. And that's called an Einstein ring. So this is an example of something that's nearly an Einstein ring. So in reality, our lenses, which are massive galaxies or clusters of galaxies, they're not so perfectly symmetric as these perfectly round wine glasses. So we might not be able to form a perfect circle, but you can see we get very close in many cases. And so this lens is fairly symmetric, even if not perfect. But when the lens is a cluster of galaxies, it's a very blobby, very, very not symmetric lens. And so you just get random arcs all over the place. And this is a nice example because you can see, so here's a galaxy here that looks like a figure 8 for the Greek letter beta. And if you look closely, well, you don't even have to look that closely. There's another copy of it. And there's another copy of it, which has been kind of further modified by the gravity from this galaxy right here. And this is another copy of it. It doesn't look exact, but it's been further lensed by this galaxy. And then there's a final copy of it right down the center. And if you look closely at the details, like you see, like not only is it the Greek letter beta, but here's this pointy end of it is extra bright, and there's like a bright knot right there. You can match it up to this image. There's the pointy end that's bright, there's the bright knot. So actually, you can go sort of pixel by pixel and say, oh, this pixel over here came from the same part of the galaxy as that pixel over there. And that gives you a lot of data to work with to constrain your lens model, and you can really figure out how the mass is distributed in the planet. And an important point here is that it's not just about the total amount of mass, but it's how the mass is distributed. So you can we can basically map where the mass is. Okay, and this is not, the following is not my work at all, but it's just so cool I had to share it with you. This is how well gravitational lensing works. Okay, so we have a cluster of galaxies here, where the mass in the galaxies is acting as a lens. And we have this pretty spiral galaxy here in the background. There's another copy of it over here. And then there's a third copy of it in the center that's highly distorted. And it's also hard to see because the light is mixed with these galaxies in the cluster itself. Now, furthermore, this arm of this spiral galaxy, and this particular copy of it, is placed to be further lensed by this cluster galaxy. And so it kind of formed a ring there. And not only that, a supernova went off in this spiral arm. And so we're seeing 4 copies of the supernova. That's this bright spot here, and that one, and that one. And not only that, the paths that the light has to take around this galaxy are slightly different lengths. So there's a little bit of a time delay. So you would never notice this with a source that has a constant luminosity. But with a supernova that rises and falls, if there's an extra time delay of like 3 weeks, then this image is maybe not at its maximum brightness yet, while this image is at its maximum brightness. So you can measure that time delay. Okay, now that I've planted the seed of the idea of time delays, you can think about the time delay between this image of the galaxy and that image and this image. And if you work through the numbers, it turns out that, so this was observed in 2014, the supernova year. And it turns out that the supernova should have been observable over here in 1998. But we can't travel back in time and check if it was there. No one was looking at it in 1998. But this image of this galaxy, the supernova should appear here in 2015. So about a year after it was observed. So Hubble Space Telescope began monitoring this area of sky, and the people who do this stuff for a living had these lens models that they thought were accurate, and they predicted where and when it would show up. And in fact, so this is exactly where it's supposed to show up. It's not there in October 30th, 2015, and it is there in December 11th, 2015. And when I show this, people often say, what? Is that really there? That's such a time. Okay, that's the discovery image. The supernova is like just starting. So it definitely is there in the gallery. Okay, so this should give you an idea of how accurately we can map mass right here. And I couldn't resist throwing in a picture from James Webb Space Telescope. So we're also, well, not me personally, but the lensing community is also really excited about James Webb and producing great images that we can do lensing analysis. Okay, so let's go back to our question about dark matter. So now that we have this great tool for mapping dark matter, let's think about dark matter in the context of doesn't really fit Occam's razor. So you can, once I invoke the idea of dark matter, then I can hypothesize, well, there's 10 kilograms of dark matter there and 100 kilograms over there. And like, I can start hypothesizing all kinds of things. So at some level, it's an extravagant hypothesis because I'm not just making one hypothesis. I'm potentially making millions of hypotheses about how much dark matter is in each area of space. So it is very attractive to try to fit a modified law of gravity to explain these discrepancies instead of dark matter. But some very smart people have tried for decades, and there's just no one's ever come up with a modified law of gravity that can explain it all because we see it in so many different environments. Right? We see it in low mass systems, we see it in high mass systems, we see it in elliptical galaxies, we see it in spiral galaxies, we see it in clusters, we see it in the cosmic microwave background. So the consensus of the astronomy community is that there really is dark matter. And okay, so now I'm going to say, like, let's try to really get a picture of dark matter and isolate it. So here's the idea. You've got a cluster of galaxies. And so one piece of background knowledge you should know is that although we call it a cluster of galaxies, only 2 or 3% of the mass is in the galaxies. About 15% of the mass is in gas, that's just filling the space around the galaxy. And then about 85% of the mass is in dark matter. Okay, so what happens when you collide these things? Okay, so the color code is dark matter is blue, gas is red, both of them together is purple, and then we have galaxies sprinkled in. So we have these two things falling together, start to overlap. The gas clouds can exchange momentum. So these are really hot gas clouds. They're like 100 million kelvins. So they're ionized, so they have electromagnetic interactions. The gas clouds can just collide and stay in the middle like a pancake. The galaxies go right on through. The space between the galaxies is much bigger than the galaxies. So they won't exchange momentum. And the question is, what happens to the dark matter? So in the standard picture of dark matter is also collisionless. So in a way, that's like the simplest thing we can hypothesize about dark matter. So a particle that doesn't do anything except have mass. So this is a model of what you should be able to see when you map the mass in one of these systems. You should see gas in the middle, and then you should see mass on either side along with the galaxy. Okay, so here's a beautiful example of where that actually is seen. This is called the bullet cluster. It's really famous, so you may have seen it before. So it's the same color coding. So we have gas that stayed in the middle like a pancake. We have a second blob of gas over here. So it turns out that this, there was a really dense blob of gas. So let me back up for a second. So here you see gas and galaxies and dark matter all together. And we think this whole collection over here, which I'm going to call a subcluster, was originally on the left and it passed through. And so by passing through, the gas clouds exchange momentum. And it wasn't quite enough momentum exchange to really completely stop this gas blob, but it definitely slowed it down compared to the galaxy. It's definitely over here. Okay, so we have galaxies here, gas here. Where's the dark matter? Well, that's where the blue is. It's over here. So the dark matter is where the galaxies are. So if you do not believe in dark matter, you still have to admit that the ratio of mass in gas to galaxies is about 5:1. So remember I said 15% of the mass that's not dark matter is in gas and 2 or 3% is in galaxies. So you should, if you do not believe in dark matter, you would have predicted that the vast majority of the mass is here where the gas is, but it's not. So this is kind of the most direct sort of empirical picture that you can see that like you really need dark matter to explain these observations. All right, so what is dark matter? We don't know that much about it, but we know more about what it isn't. So we know it's not made of protons or neutrons, and I have some backup slides on that if you're really interested, but I decided we didn't have quite enough time to go into that. But that's a pretty strong statement, right? So when I say dark matter, you could say, well, if I just put a rock out in interstellar space, that's pretty dark. No one's going to see it, right? Could be anything. But no, this actually, we have a very strong argument that it can't be made of anything that's made of protons and neutrons. Does not interact with light. So it's not just dark in the sense that it doesn't emit light, but it also doesn't block light or scatter light from background sources. Yeah. How do you define light? Protons? What else did you have in mind?
Just visible light.
Oh yeah, there's no wavelength of light that we have any evidence that interacts with dark matter. Any part of this thing.
That's true. What was the blue stuff in the previous slide that we were showing?
So I did skip a bunch of steps. So, okay, so the idea is, let's go back here. All right. This, although it's not a perfect Einstein ring, you can tell from the curvature of these arcs that like there must be a bunch of mass centered right here in order to make these distortions. I don't know if that's clear to someone that I just explained this to. Let's go back. Okay. So here's a very clear example. This is like, if you see something like this on the sky, that's almost a perfect Einstein ring. You can calculate exactly how much mass is inside this ring and where the center of mass is. It's at the center of the ring. Are you with me so far?
I'm struck. What exactly is causing the blue to be shown?
Yeah, so the blue thing here is a background galaxy. So you can take a spectrum of this. It's just a galaxy. But no galaxy in the universe actually looks like a ring like that, right? But without some kind of extra distortion. So the distortion that's coming in is from, yeah, I should have explained this better. This galaxy is a foreground galaxy. And this galaxy is a background galaxy, and we know that from taking spectra and getting the redshifts. And so the shape of this background galaxy is super peculiar because it's been distorted by the mass. Let's go back. So here I'm shining see how there's these arcs here? So there's a background source of light. It's basically right down the axis, but we're seeing the images way off axis because of the optical effect. Maybe this is even better. You can tell this is graph paper with circles on it. You can see how distorted it is. So this, you look at this, if you turn it this way, it has the shape of gravitational potential, right? So this is why this wine glass is such a good analogy. So you put this in front of a light, you see something like a circle, so you can then infer exactly how much gravity there had to be to bend it like that. Still look puzzled. This, okay. There was a hand up over there. Yes.
Sagittarius A star, that's supposed to be the big powerful thing out there in the, south southern sky right now. Is it too close for gravitational lensing to show up for things around it? Because what I've read or perceived is a lot of these gravitational lens phenomena are way far away.
Yeah, that's a great question. So first of all, the center of the Milky Way has like 30 magnitudes of extinction, so it's really hard to be very impossible to observe in the visible. Maybe in the radio it'd be easier to observe. But then you have the problem that, okay, all this gravitational stuff I'm talking about really has nothing to do with black holes. Because when you get your photons too close to a black hole, they can fall in. So lensing by black holes like Sagittarius star is a whole different ballgame, and it's really complicated. And so the center of the Milky Way has lots of stuff going on too. So I don't think we'll ever observe lensing by Sagittarius star. Sure. Yeah.
I don't know if we can get to this, but at what scale do we see gravitational lensing? We don't see it in the solar system. We don't see it in star clusters. There's up to galactic and distances. See.
So yeah, it's a really good question. So famously, the confirmation of general relativity actually came from an observation of gravitational lensing in the solar system, but it's not something you can see with your naked eye like this. But when light from a background star passes close to the sun, its path gets bent by 1.8 arc seconds. And how are you going to see that when the sun's in the way, right? It's going to be blinding. So you wait for a total solar eclipse, and then you can map the stars that are projected near the sun, and then you map them when the sun's not there, and you see that they've been shifted a little bit. So it actually does happen in the solar system, just not very dramatically. It also happens in the Milky Way. So like if you have a star, I don't know, 5 kiloparsecs away, and you have some compact object like a black hole between us and the star, that does cause a tiny little Einstein ring, but it's so tiny that you can't see it. But what you do see is the Einstein ring is brighter than the point of light that you would have without the lens. Again, this is very useful. Come up and play with it afterwards. You'll see that instantly. So when you magnify the point into a whole ring, you just get a whole bunch more total light. So when you can see the star get brighter and then fainter as a black hole passes in front. That's called microlensing, because the size of the Einstein ring is too small to see. If you see the total flux from the star increases. So it does happen on all scales, but these kind of fantastical pictures only happen on extragalactic scales. Oh, some really good questions. Keep them coming. Yeah.
Is the blue color real, or is that?
That's real. So very distant galaxies do tend to look blue because they're redshifted. Now that sounds like a contradiction, right? But when you have a lot of redshift, what you're doing is you're shifting the rest frame ultraviolet into a blue for us. So galaxies are forming lots of stars, emit lots of ultraviolet, and these distant galaxies do tend to be forming lots of stars, and so that ultraviolet shifts into our blue, so they look blue.
Yeah, I got a question.
Yeah.
how far away distance are the two different objects?
I don't know off the top of my head, but you know, this could be like a gigaparsec and the source could be like 3 gigaparsecs. Now, I still didn't answer, okay, this blue is different, right? So that's something I didn't explain about. All right. Let's go back. So now that you have this idea, hopefully that like an arc tells you where the center of mass is and how much mass there is. Now, we can sort of drill down and say, okay, we know there's got to be a lot of mass here because we see arcs bent like this. But we could also go way, whoops. We can go over here and kind of get an idea of like, if there were happens to be locally a lot of mass right here, we would see this arc bent the other way. So on. So you can see, so this is, so by sort of statistically tabulating the amount of arciness everywhere, we can figure out how much mass is at each line of sight in the sky. And then we build up a map of how much mass is there. And this, come on. Okay, so this blue is completely false color. This is the result of that statistical analysis, just telling us where the mass is centered and how much it's spread out. So two very different uses of the color of the data. Okay, so let's try to think of what this thing is. Well, presumably it's some kind of particle, and it's not a particle that decays because it's been around for 14 billion years, the age of the universe. So we're going to call it stable. We know, is that a question? No. Right. It's not moving at very high velocity because we know these dark matter particles remain in the gravitational potential. Like the escape speed of the Milky Way is 600 kilometers per second. Milky Way has plenty of dark matter. So we know that these aren't like really fast particles like photons or neutrinos. And dark matter even collects in the gravitational well of galaxies with much lower escape velocities. So we know the collective density of dark matter is this really small number. And we know that dark matter doesn't interact with already known particles, except really, really weakly. So this gives theorists, I'm not a theorist, so I can make fun of them. You know, this is a field day. Like if you give them any room to like make some really complicated model, like they'll come up with all kinds of different explanations. And then we observers have to go and test them all. So there's like many ways to test depending on what the model is, the best way to test it can be different, right? So so this introduces this idea of like, we're going to just test the extent to which two dark matter particles interact with each other. So that's something that can't be tested like in these underground laboratories that search for dark matter particles that, you know, Earth is presumably flying through a sea of dark matter particles. And, you know, if we can get it to interact with a human built detector, that's great. But this would be a different thing. It's like, do two dark matter particles interact with each other? Do they collide? So I kind of saw this, you've heard of the Large Hadron Collider. So these clusters of galaxies that collide are the large dark matter colliders. So if the dark matter particles do exchange momentum, this is now a modified picture. The galaxies are collisionless. The gas is very collisional, but the dark matter is a little bit collisional, then it'll begin between. And you can already apply this argument to the bullet cluster. The bullet cluster does technically have a little bit of an offset, but it's within the error bar. So that allows you to put an upper limit on the cross section. In particle physics terms, it's 2 barns per GeV. Now, a barn is a unit of area that particle physicists came up with as kind of a joke to mean a really large cross section. So this is like, this is the same cross section with which like 2 neutrons will interact with each other. So it's like a pretty big cross section in particle physics terms, but because we can't do controlled experiments, we still don't know that about dark matter, if they even interact at the level 2 neutrons would interact with each other. So we want to use these clusters of natural colliders. All right, so now I'm going to talk about 2 ways to find more clusters like the bullet cluster and study them. So one way is with radio selection. And I have changed the color coding on you now. So this is, radio astronomers have this thing that they call a relic, which is an extended radio source on the outskirts of the cluster. And here we see in red is X-ray emission. So remember the gas is really hot and emits X-rays. And the solid contours are radio emission. And so this is a classic radio relic. And what we think it is a shock wave. So these two things pass through each other supersonically, and that sets off a shock wave in that gas. And so you can see kind of the edge of it. Think of it as like a spherical shell expanding. And that's the edge of it. This one is called the sausage because it looks like a sausage. And this one is called the toothbrush. It's just another case of we have this extended radio emission on the outskirts of the cluster. So radio surveys are doing a good job of covering the whole sky and discovering these kinds of things. So I embarked on this project about 10 years ago, more than 10 years really, to follow up these known radio emitting systems and to find out where the galaxies are and to measure the galaxy velocities and figure out if it really was a collision of two galaxy clusters. And if so, how fast was the collision? How many years ago in the past was what we call pericenter, when the two clusters were maximally overlapping? And that kind of just start to model what this collision looked like, what angle we're viewing it from, that kind of thing. Okay, so for this, we use the Keck telescope. This is an amazing observatory, two 10-meter telescopes. They do have star parties at the 9,000 foot elevation below, so the summit is at 14,000. But if you ever go to Hawaii, that's something you might consider joining one of those parties. And I use this instrument. Yes.
Can you buy time at those observatories as a private person?
No.
Willing to write a check?
I mean, if you're a billionaire, maybe, but okay, I won't answer that in any more detail. If you have $1 billion, come talk to me after. The University of California is a major partner in basically UC astronomers designed this thing and helped build it. That was before I joined UC, so I don't get them credit. This instrument called DEMOS is a multi-object spectrograph, and it is amazing. If you want to see some raw data from it, come up afterwards and I'll show you, but again, I didn't have time to plan this into the talk. But basically, I can get spectra of like 120 galaxies at once. So that's perfect for a cluster of galaxies where I want to know the velocity of every galaxy, if possible. And in about an hour, I can get redshifts of 100 galaxies. So this is what a spectrum looks like. And so this is little data analysis tool I built. So the blue is the data, and the orange is the best matching template. And so basically, you shift the template. The more you shift the template to the red, the bigger the redshift of the galaxy. And if there's a mismatch in the heights, don't worry about it. That's because it just says that the throughput of this optical system is less than what I had in my code. So we got fewer photons, but as long as the features line up horizontally, you're good. You got the right redshift. And so what I show in the lower panel is kind of removing the overall slope of it. So it's overall flat, which really emphasizes the wiggles, and just an amazing match between template and data. So the redshift of this galaxy is 0.296403 plus or minus 10 to the minus 5. So this is really, Keck plus DEMOS is really an amazing machine for getting redshifts. Okay, so what do we find? So this is an interesting candidate. The name of this cluster, well, it is the sausage, as you saw. But another name for it is CISA J2242. Okay, so these are the coordinates. CISA stands for clusters in the zone of avoidance. So why am I studying a cluster in the zone of avoidance? There's a lot of extinction and it's hard work. Well, the radio astronomers that gave me their sample don't care about the zone of avoidance because the Milky Way doesn't absorb radio waves from distant galaxies, so it's transparent. So this was like an ideal target, except that it happens to be sitting behind like a magnitude of extinction. But, and also, every source of light you see, almost every point of light you see here is actually a star in the Milky Way, and not a galaxy that I'm interested in. So you have to zoom into the raw data, and you see that there are galaxies in there. And you can also see the X-ray radio emission. So the white contours are, again, I changed the color coding, sorry, where the galaxies, right? So this is where the galaxies are. So by doing this analysis, we proved that yes, this is a collision of two galaxy clusters. It left the X-ray emitting gas in the middle. And we measured the velocity of the galaxies in this cluster and the galaxies in that cluster. And what do we come up with? So this is a histogram of velocities in one subcluster and the other, and they look identical. So it looks like they're going at exactly the same velocity. And I don't know if you think that's disappointing or exciting, but let me remind you, what we can measure with the Doppler shift is the line of sight velocity. So what that means is this subcluster, we can only measure the component of velocity that's coming towards us or going away from us. Similar with this one, and we see that there's no difference in that component. So what that means is any motion that these two are undergoing must be in the plane of the sky. That's actually really good for us. So that means that we don't have to worry about projection effects. If there is a separation between dark matter and galaxies, we'll see it because it's going to be clearly laid out in the sky. Whereas if the merger was along the line of sight, okay, now you guys are the observer, the merger is doing this, you're not, if there is a separation between dark matter and galaxies, you wouldn't be able to see it because it'll all be hidden along the line of sight. So this is exactly the kind of thing we're doing. And we did set a rough limit on the dark matter interaction from this, not as good as the bullet. Here's an interestingly different example, the toothbrush. And you can see the radio data has gotten better at higher resolution. It really looks amazingly like a toothbrush there. What we found, so in this case, white contours are telling you where the mass is instead of the galaxies. But it turns out in this one, where the mass is basically matches where the galaxies are. So I didn't bother to show both. What we see here is multiple mass peaks. So we see about 5 different mass peaks. This is a really complicated interaction that I'm not smart enough to model. I'm like, there's no way I can keep track of 5 galaxy clusters interacting. That actually sort of explains why this shock is so linear. So in the case where you have just 2 things that went through each other, you would expect sort of a spherical shock wave. But if you have multiple bodies interacting, that can change the shape of the shock point, and that explains it as more linear interaction. So this is something that we just threw out of our sample because it's too complicated. Here's a couple more examples. This one really does look like the bullet in X-ray. So something I didn't tell you before is that the amount of X-ray emission goes as the density of the gas squared. So if you have a really high dense core of gas, it's going to be very bright in X-ray. And that's actually what we call a bullet. It's just that dense core of gas. And so in this case, the gold is the radio, the white is the galaxies and the mass, and then the color scale is the X-ray. This is like a low mass bullet cluster that we discovered. This one here is kind of interesting because it's got, this is a cluster that's been extremely well studied by HST, but the HST field of view is small. So HST focused on a little box like this. And no one ever zoomed out enough to notice that there was another cluster of galaxies out here that didn't have any gas associated with it. So our model is that this cluster originally came from up here and passed through and had all the gas stripped off. Okay, now, when did I start? How am I doing that time?
7:48. Used to be
When did I start?
probably 10 minutes after
Okay.
7.
All right, so let's switch gears. So that was the whole project I did, kind of wrapped up a few years ago on the radio selected clusters. Now I'm going to show you the second way that we're going to find more bullets, which is optically selected clusters. Yeah.
What did the blue designate in that previous?
The blue to white is a false color X-ray image. Okay,
Question?
yeah,
Does that bullet, the brightness also indicate linearity? Is that going across or? you know,
yeah,
is
it's
that-
going through the shape of this. It's like a ship going through water. It's like
Okay,
a
so
bow wave.
we're getting
Yes.
linearity out of it.
Yep, you can tell the direction we're from there. Okay, the second way that I've gone about trying to discover more of these is through optical surveys. Because if I am given a target that was discovered in the radio, and then I look optically and it's this horrible mess of 5 different interacting things and it's too complicated, then I kind of wasted my time, right? why don't I start with things where I know there's two groups of galaxies from the beginning, using these amazing optical sky surveys that cover the whole sky now. So I'm gonna just spend a few minutes showing you how amazing optical sky surveys are today. So this is the same area of sky in these three panels. This is from the digitized sky survey. So ultimately, these are from photographic plates taken around 1970 that were digitized. This is the Sloan Digital Sky Survey. So you can see a lot more. You have better angular resolution. You have multiple wavelengths. So this was data taken in the early 2000s. And this is data I took as part of what's called the Deep Lens Survey. So this was this is 18,000 second exposure with a 4-meter telescope in R band and 9,000 in 3 other bands. And so you can go really, really deep. And so this is, again, this is the same part of sky. So with Sloan, you're just seeing, oh, that's the brightest galaxy there. With this deeper imaging, you're seeing so much more detail. Okay, but with this deep lens survey, we went really deep, but we couldn't cover much sky. Because we, when you do 18,000 seconds in one pointing, you're not going to cover much sky. So, but today we have these great sky surveys that go deep and wide. So I'm gonna suggest you go to this website, and I'm gonna go there now with you. It's too amazing not to share. Okay, so let's go. Let's say my favorite ABEL cluster, ABEL 56. So by default, it's just showing the digitized sky survey. Let me zoom in a little. Okay, does that look much like a galaxy cluster? I don't know. Maybe there's a couple there and a couple there. It's not like much. Okay, let's go to this slow digital sky survey. Okay, that's better. It does look a little better on that screen than my left exactly, but you can see more. But still not overwhelming. Okay, now after Sloan Digital Sky Survey, there's a survey called Pan-STARRS. And by the way, the Sloan Digital Sky Survey covers 10,000 square degrees, so about 1/4 of the sky. Pan-STARRS covers 3/4 of the sky, and a little bit deeper. And that's what we're doing. So this tool Aladdin is great. Yeah, so now it's looking for the other. Come on, you can do it. Oh, darn. My big reveal. I don't know if it's gonna work. Okay, let's go to the most recent survey, the DESI Legacy Survey. Let's click on it and see if it loads. Oh no. All right, maybe I'll come back to this at the end of my talk. But if you want to play with it yourself, just Google Aladdin with 1D Sky Atlas. It's really an amazing tool for seeing the sky at different wavelengths and very deep. That's the hazards of a live demo. And I'm going to give a shout out to a survey called LSST, which hasn't started yet, but it's using this newly constructed telescope, the Vera Rubin Observatory. It's going to cover 20,000 square degrees to this depth. So we did this back in the 2000s. It's kind of a precursor to LSST. This is 1/50 millionth of the amount of sky that's going to be covered by LSST. So that's going to be another amazing. Okay, so we have all these images. Let's use them to discover pairs of galaxy clusters. So, and once I discover pairs of galaxy clusters in the image, then I'm going to go to X-ray archives to see if there's X-ray data. And I want to see if the X-ray peak is between the two galaxy clusters. So here's a couple of examples where I know this doesn't look like super impressive as a galaxy cluster, but it is. There are two subclusters here, and there's an X-ray peak in the middle. Here's another case where I think this thing is actually a star, so don't pay any attention to that. But you have a bright galaxy here, and some less bright ones, and you have a subcluster here, and an X-ray peak in the middle. So this is exactly the kind of thing I want to study in more detail with my access to this amazing spectroscopy machine. And the one I want to show in a little more detail is called ABEL 56, the one that I was trying to show you. This one happened to have archival HST data. So this is something I also want to mention, that, you know, every image ever taken by HST is in an archive. And same with James Webb. And it turns out the same is true for any big ground-based observatory. So any data ever taken with the Keck telescope is in an archive that you can search. So if I make a proposal and I get my time on Keck and I get my data, I have exclusive access to it for 12 months. But after that, anybody in the world can download and analyze it. So it's getting to the point where there's like such a critical mass of archival data that you can start to do, you can make new discoveries just from archival data without writing a proposal and doing the observing. So in this case, there was an archival HST image of this cluster. So you might recognize the shape of it from before, but now you can see a lot more detail. And the red is the X-ray contours. Okay, so we got a lot of data on this and studied it in much more detail, and this was the final results. So we have the white is where the mass is, and you see two clumps of mass with the X-ray peak in the middle. The clumps of mass mostly coincide with the galaxies, but not exactly. There's a little bit of an offset. And then we also took radio data, and we found this structure out here, which may or may not be a shock. The fact that it's attached to a radio point source means that there's an AGN there, but it's not clear if this end of it might be a shock. So more work is needed to understand the radio data, but right away with the mass map and the galaxy positions and the gas position, we were able to put an independent constraint on the cross-section of dark matter from this that's sort of competitive with what the bullet did, not quite as good as what the bullet did. But the idea is that we're building up an ensemble of these things so that, you know, if we get a dozen of these things and combine it with the bullet, we'll be able to get a much better estimate in total. And just a few words about the modeling of these things. So, like I said, I kind of sell this as like the Large Dark Matter Collider. It's a lot like the Large Hadron Collider, right? But that sweeps a lot of details under the rug. At the Large Hadron Collider, you have instruments all over looking at the collision from different angles. You know exactly where the collision took place, when it took place, what the speeds of the particles going into it were. In my case, I know none of that. So actually, most of the challenge to what I'm doing is in modeling the collision itself. So how many, okay, so I see these two groups of galaxies, and they're separated by, let's say 400 kiloparsecs on this image. But are they truly separated by 400 kiloparsecs? Or maybe they're separated by more than that, and I'm just seeing in projection some fraction of that. And I need to model all that stuff. And so the way I do it is I go into cosmological simulations that include lots and lots of clusters. And I pick out pairs of clusters that look like my system. And once I've picked out a pair of clusters that could be my system, I can trace it back in time and see the whole trajectory. And so this is a bunch of merging clusters picked from a cosmological simulation. So the different colors, just each color represents a different system. The opacity of the line represents how well it matches my data. And you can just see them fall together from a great distance, reach almost zero separation, and then come back out to the separation that we observed today. So this has been a great tool for modeling these things. And just like there's lots of archival data, there's lots of archival simulations. So the experts who make these massive simulations of the universe also make their simulated data available for anyone to access and play with. So that's a really nice feature of modern astronomy. Okay, so in summary, I hope that I've given some sense of how the bullet cluster gives us a first picture of dark matter without all the usual normal matter obscuring it, and that it gives it allows us to say something about the extent to which dark matter particles interact with each other. And I hope I convinced you that the bullet cluster isn't the only cluster that we can do that with. We can do that. We've been discovering many other similar clusters, and so we can start to get much better statistics. And to make sense of all this really requires panchromatic observation, so not just optical, but radio and X-ray. And that makes it fun to assemble all these different things in one unified picture. And so another aspect of the unification here is that, you know, hopefully astronomy will be able to say something to physics about what dark matter is, about the particle nature of dark matter, just by studying the behavior of dark matter in the wild. So I really think this is a great example of how astronomy and physics can work together. Thanks for your attention.